Imagine two particles miles apart, yet inexplicably linked, their fates intertwined. This isn't science fiction, it's quantum entanglement. Welcome to the enigmatic world of quantum physics, a realm where the laws of nature as we know them take a back seat and the extraordinary takes the wheel. Among these extraordinary phenomena is something called quantum entanglement. But what is it exactly? Picture this: two particles are created at the same point and instant in space. These particles are entangled, a term in quantum physics that means the properties of one particle are directly connected to the properties of the other, no matter how far apart they are. It's as if they are two halves of the same whole. In the world as we know it, this seems impossible. After all, how can the state of one particle located in London, for instance, instantly affect the state of another particle in New York? But in the quantum world, this isn't just possible, it's a reality. And it's not just about distances on Earth. Even if these particles were on opposite ends of the universe, the change in one would instantaneously reflect in the other. It's a concept so baffling that even Albert Einstein famously referred to it as spooky action at a distance. Now, here's where things get even more interesting. If we can harness this spooky action, this instant communication between particles, could we potentially use it for faster-than-light communication? Could quantum entanglement be the key to breaking what we thought were unbreakable cosmic speed limits? So, could this phenomenon lead to faster-than-light communication? Let's delve deeper. To understand quantum entanglement, we must first visit a paradox posed by Albert Einstein, Boris Podolsky, and Nathan Rosen. This trio of physicists questioned the completeness of quantum mechanics, formulating a thought experiment that became known as the Einstein-Podolsky-Rosen, or EPR paradox. At its core, the EPR paradox is about the strange correlations observed in quantum particles. Imagine two particles that are entangled, a fancy quantum term meaning their properties are intrinsically linked. Even when separated by vast distances, a change in one particle seems to instantaneously affect the other. Einstein was skeptical of this phenomenon, dubbing it spooky action at a distance. He argued that there must be hidden variables at play, unseen factors that determine the outcomes of quantum measurements. Yet, as we now know, quantum mechanics embraces this spooky action, accepting the entanglement of particles as a fundamental part of the quantum world. This led to a revolutionary theory known as Bell's theorem, which we'll delve into next. John Bell, a physicist, proposed a theorem that shook the foundations of quantum physics. Now, let's delve into what that theorem is all about. Bell's theorem, proposed in the mid-20th century, deals with the fascinating and, at times, mind-boggling world of quantum entanglement. This theorem posed a direct challenge to Einstein's local realism, the idea that physical processes occurring at a particular place should only be influenced by their immediate surroundings. Bell suggested that if the world obeys local realism, then there are limits to how correlated two particles can be, no matter how entangled their quantum states. But if the world is truly quantum, these correlations can be stronger. This became known as Bell's inequality. But how could we test this inequality? This is where the quantum experiments come in. A series of cleverly designed experiments known as Bell tests were conducted to test the predictions of Bell's theorem. These experiments involved creating pairs of particles that are quantum entangled, meaning their properties are linked no matter how far apart they are. The particles are then separated and measured. According to quantum mechanics, the measurement of one particle instantly affects the state of the other, no matter the distance between them. So, what were the results? Time and time again, these experiments have shown correlations between particles that are stronger than what is allowed under local realism, confirming the predictions of quantum mechanics over those of Einstein's local realism. The results of these experiments have profound implications. They suggest that the world is fundamentally interconnected on a deep quantum level, a concept that challenges our everyday experiences and understanding of the universe. These experiments provided evidence of the strange, interconnected world of quantum mechanics. But as with all things quantum, the full understanding and interpretation continue to be subjects of ongoing debate and research. But one thing's for sure, the quantum world is a lot stranger than we could have ever imagined. So, how does quantum entanglement tie into communication speed? Let's break it down. Quantum entanglement, a bizarre phenomenon exclusive to the quantum world, is where two particles become intimately entwined. This entanglement implies that a change in the state of one particle instantly reflects on its partner, regardless of the distance between them. This is where things get really intriguing. Imagine this: you're on Earth and your friend is on Mars, and you both have a pair of entangled particles. If you measure your particle and find it spinning in a certain direction, the entangled particle on Mars will instantaneously start spinning in the opposite direction. And when we say instantaneously, we mean just that. This change happens faster than light could travel between the two locations. Now, does this defy Einstein's theory that nothing can travel faster than light? Not quite. While it's true that the information about the state change seems to travel instantaneously, it's important to note that you can't use this phenomenon to send information without a classical signal accompanying it. So, we're not breaking any cosmic speed limits, but we're certainly pushing the boundaries. But what if we could harness this property for communication? If we could find a way to manipulate the state of these particles, we could theoretically create a communication system that operates faster than anything currently available. In essence, we could potentially send messages instantaneously across vast cosmic distances. This could revolutionize not just our understanding of the universe, but also how we interact with it. Interplanetary communication could become as instantaneous as a text message, enabling real-time communication with astronauts on Mars or even further. However, it's crucial to remember that while the theory is enticing, the practical implementation of such a system is fraught with challenges. Quantum entanglement is delicate, and preserving the entangled state over large distances is currently beyond our reach. This leads us to the concept of quantum teleportation. But before we delve into that, let's take a moment to appreciate the astounding possibilities that quantum entanglement presents for the future of communication. Quantum teleportation might sound like a concept straight out of a sci-fi movie, but it's a real scientific theory. Quantum teleportation, in essence, is the process of transmitting quantum information from one location to another, leveraging the peculiar properties of quantum entanglement. It's like faxing, but instead of paper, we're dealing with quantum states. Let's break it down. Quantum entanglement is a phenomenon where two or more particles become interconnected. This interconnection is so deep that the quantum state of each particle is immediately connected to the state of the others, no matter how far apart they are. This is where quantum teleportation comes in. It's a process that transmits the state of a quantum system from one location to another without any physical movement of the system itself. The term teleportation might be a bit misleading, though. It's not about Star Trek-style transportation of matter, but rather about the transfer of information. Here's how it works. Let's say we have two entangled particles, particle A and particle B. If we make a measurement on particle A, we immediately know something about the state of particle B, even if it's light years away. Now, if we want to teleport the state of a third particle, particle C, to particle B, we would first entangle particle C with particle A and then measure them both. This will cause the state of particle C to collapse onto particle B, effectively teleporting the state of particle C to particle B. But remember, it's not the physical particles that are being teleported, but their quantum states. The process destroys the original state of the particle being teleported, so it's not like we're creating a clone. Instead, we're transferring the information about the state of one particle to another. So does quantum teleportation mean we can send messages instantly across vast distances? Unfortunately, no. The process of quantum teleportation still requires classical communication, which is bound by the speed of light, to complete. But it does open up fascinating possibilities for secure communication and advanced computing. If we can teleport information, can we also teleport matter? That's a question for another day. The potential of faster-than-light communication is mind-boggling, but it's not without its challenges. The idea of information traveling faster than light is a tantalizing concept. It would revolutionize our understanding of communication, but it's not as simple as it sounds. The primary challenge lies in the realm of causality. In simple terms, causality is the principle that an effect cannot occur before its cause. It's a fundamental concept in physics, and faster-than-light communication threatens to violate this principle. Imagine if you could send a message to someone on the other side of the planet, and they receive it before you even hit the send button. It's a mind-bending concept. But that's the kind of possibility we're dealing with when we talk about faster-than-light communication. Now, quantum entanglement does not necessarily violate causality, because no usable information is transferred faster than light. The state of the entangled particle changes instantaneously, but you can't control the state that it collapses into, so you can't use it to send a specific message. However, the story doesn't end there. Some physicists have suggested that it might be possible to use quantum entanglement to send information faster than light, using a concept known as quantum teleportation. But this is still a highly theoretical area of research, and we're far from having a practical quantum teleportation device. Moreover, there are also technical challenges. Quantum states are extremely delicate and can be easily disrupted by the environment, a problem known as decoherence. Maintaining entanglement over large distances is a significant challenge, and we may need to develop new technologies like quantum repeaters to overcome this. In conclusion, while the potential of faster-than-light communication through quantum entanglement is exciting, we must tread carefully. Theoretical and technical challenges abound, and we have much to learn about the strange and wonderful world of quantum physics. As we venture into the realm of quantum entanglement, the lines between science fiction and reality continue to blur. So where does this leave us in terms of the future of communication? Let's imagine a world where quantum entanglement is the backbone of our communication systems. This might sound like science fiction, but scientists are already exploring this intriguing possibility. Quantum entanglement could open the door to quantum networks, where information is transported instantaneously across vast distances, effectively breaking down the barriers of time and space. Imagine sending a message to a friend on Mars without any delay. You would be able to have real-time conversations with astronauts exploring distant galaxies, or even communicate securely with quantum cryptographic systems, impervious to any kind of eavesdropping. Sounds exciting, doesn't it? But this is not without its challenges. The theory of quantum entanglement might be sound, but its practical implementation is a whole different ballgame. The biggest hurdle is maintaining entanglement over long distances, a problem known as decoherence. This is where quantum repeaters come into play, acting as a bridge to maintain entanglement and ensure secure communication. Moreover, integrating quantum communication with our existing classical networks presents another set of challenges. We would need to create a system where classical and quantum communication can coexist seamlessly, a task that requires both technological innovation and a rethinking of our current network infrastructures. But despite these hurdles, progress is being made. Real-world quantum networks are slowly becoming a reality, with projects underway to connect research facilities and universities. These networks will act as testbeds for new quantum technologies, paving the way for a future where quantum and classical communication coexist. This future might not be as far away as we think. With the rapid pace of advancements in quantum physics, we could see the dawn of a new era in communication within our lifetimes. An era where quantum entanglement enables faster, more secure, and more efficient communication, transforming the way we connect, collaborate, and explore the universe. Quantum entanglement presents a fascinating frontier for scientific exploration, promising to revolutionize how we understand and utilize communication. In this incredible journey through quantum entanglement, we've traversed from the realm of the tiny to the vast expanse of the universe. We started by understanding the basics of quantum entanglement, a phenomenon that left even Einstein puzzled and led to the famous Einstein-Podolsky-Rosen paradox. This paradox, born from a thought experiment, challenged the very completeness of quantum mechanics. We then delved into Bell's theorem and the experiments that followed, confirming the non-local correlations predicted by quantum entanglement. These experiments showed us that the world of quantum mechanics is indeed as strange as it seems, with particles being intertwined in a way that transcends our classical understanding of space and time. As we moved on, we explored the potential implications of quantum entanglement for communication speed. We learned that changes to one entangled particle could instantaneously affect its partner, regardless of the distance separating them. This phenomenon could hold the key to faster-than-light communication, a concept that, if realized, would revolutionize the way we communicate. However, we also acknowledge the challenges and limitations that come with utilizing quantum entanglement for communication. Issues such as decoherence and the need for quantum repeaters remind us that we are still in the early stages of understanding and harnessing this fascinating phenomenon. As we look towards the future, we are excited by the potential applications of quantum entanglement. From quantum networks to secure communication, the possibilities seem endless. Yet we must also grapple with the theoretical implications of faster-than-light communication and the challenges it poses to the causality principle. The mysteries of the quantum world continue to unravel, promising to reshape our understanding of the universe and our place in it.